In this video, we'll take a look at an example where we apply Green's theorem to find the value of a line integral. Okay, so in this problem, we're presented with the line integral over the curve C shown in this diagram here. So the vector field has components P and Q. So this is the P component, this is the Q component, right? So in this problem, the line integral is written in this form. So in this form here, but again, it's just a way of writing the line integral. It could have also been presented in this form. But in any case, this is the P and Q components of the vector field. So the curve C is a piecewise smooth curve with the C1 portion being the graph of y equals x cubed from the point 0, 0 to the point 1, 1, and the curve C2 is a straight line segment from the point 1, 1 to the point 0, 0. So notice that the curve C is simple and closed, and also it's oriented counterclockwise. And so the conditions for Green's theorem is satisfied, so everything is set up properly. So when we apply Green's theorem, we're going to calculate a double integral instead of the line integral. So we don't necessarily have to parameterize the curve C, right? So what we need to do is to describe the region R, which is the interior region. And notice that we can calculate it as a type 1 region, right? Because if I view this line as the top boundary and then this curve as the bottom boundary, so a type 1 region, you have functions for the top and the bottom boundary. Okay, so this is type 1. Okay, so what is the interval for x? Well, x goes from here to here, which is from 0 to 1. And what is the boundaries for y? Well, the top curve is y equals x, and the bottom curve is y equals x cubed. Okay, so let's just make a note of this, right? So this is the bottom of the region, and this is the top of the region. Okay, so so we have the region set up. Again, before we can apply Green's theorem, we have to calculate some partial derivatives, right? So this calculation here. So we need the partial of Q with respect to x and the partial of P with respect to y. Okay, so what is the partial of Q with respect to x? So the derivative of x cubed is 3x squared, and then the derivative of this, so the derivative of 3x is just 3, and then the y squared just stays there because we're differentiating with respect to x, and then here derivative of this with respect to y is just 3y squared. Okay, so that's dq dx and dp dy, and then now we need to subtract them. So that's just 3x squared plus 3y squared minus 3y squared, which is equal, so this cancels this, so you get 3x squared. Okay, so now everything is set up. We're ready to apply Green's theorem. So the basic idea again is instead of calculating this line integral, Green's theorem says that it should be equal to the double integral over the region R of the partial of Q with respect to x minus the partial of P with respect to y. And okay, so now we're calculating the double integral instead, right? So we have to set up the double integral. What is the region of integration? So x goes between 0 and 1, y goes between x cubed and x. And we've already calculated this partial derivative, right? So it's just 3x squared. The inner integral was y, the outer integral was x. Okay, so we just need to calculate this double integral, and taking a look at it, it doesn't look like it's too difficult to compute. Right, so here we're integrating with respect to y, so we're thinking of x as being constant. So the whole thing is just thought of as a constant, so the antiderivative is 3x squared, 3x squared y, evaluated at the endpoints. Okay, so we got to the integral from 0 to 1. Now we plug in x. So what do we have? We're plugging x in for y, right? So it's 3x squared times x minus 3x squared times x cubed. And then going on to the next page, so let's simplify this. So 3x squared times x is 3x cubed, and then x squared times x cubed is x to the 5th. Okay, so then here the antiderivative again is just the power rule, so you get 3x to the 4th over 4 minus 3x to the 6th over 6, evaluated from 0 to 1. And then now we just plug in the numbers, right? So plugging in 1, you get 3/4. Plugging in 1 here, you get 3/6, which is 1/2. And minus, plugging in 0, you get this is 0, and then this is 0. So the whole thing is just 3/4 minus 1/2, which is equal to 1/4, or 0.25. Okay, so so we calculated the double integral as equal to 1/4, but again, Green's theorem says that the line integral and the double integral should calculate to the same thing, and so the value of this line integral is also 1/4. Okay, so so we applied Green's theorem in this problem. However, technically, you don't have to use Green's theorem, so it's possible to calculate this line integral directly. However, you have to parameterize the two curves C1 and C2 and calculate it as two separate line integrals. So below the calculation that we did here, I've given a brief description of how to calculate the line integral directly, right? So as I said before, the curve C is broken into two parts, C1 and C2. So you have to calculate them separately. To calculate the line integral, you have to parameterize the curves. So C1 would be parameterized like this. C2 would be parameterized like this. And then you can proceed to calculate the two line integrals. However, this calculation is not too difficult, but it is somewhat tedious to set everything up. And so in this problem, applying Green's theorem allows us to save a bit of time. Okay, so that's example 1.